Okay, so hello everyone. Welcome to episode 58 of Warsaw Quantum Computing Group Meetups. My name is Pavel. I'm the organizer and I will be the moderator today. And we have pleasure to host uh, another great speaker, Dr. Jarosław Duda from Jagiellonian University. And today he will tell us about two-way quantum computers. This is the idea that he proposed for adding CPT analog of state preparation. And in theory, such two-way quantum computers will be able to solve NP problems. But that's just a theory for now. Before we proceed, just a few announcements. This meeting is recorded. Hopefully the video will be later available on our YouTube channel. And we already agreed with Jarek that if you have any questions, you can raise your hand. Feel free to interrupt so we can make this lecture interactive. But you can also post your questions on the chat, and at the end there will be also a Q&A session. So there'll be also opportunity to ask questions. Before we proceed, I would like to thank our strategic partners for supporting us: Sonovero R&D, Onyx, Quantum.io, Cogit, and ThinQubit. We also have our honorary partners who support us in advertising the events. We also thank them for the support. And with this, I will stop sharing my slides. So Jarek, so first of all, thanks for accepting our invitation to give this talk. And if you are ready, the Zoom is yours.
Okay, thank you very much for the invitation and for coming. So, as mentioned, I will talk about two-way quantum computers. Yes, so which at least in theory in this moment, but I will show many arguments that it should be possible. That in theory, that as we use usually the state preparation, it, the fundamental physics, the quantum field theorem is believed to be CPT symmetric. So should also allow for the counterpart, the symmetric counterpart, which would allow for much more powerful quantum computers control from both sides, not only from state preparation, but also from the other side. So in quantum mechanics, quantum computers, at heart we have the unitary process, which is symmetric, yes. However, the boundary treatment, the state preparation and the measurement are asymmetric, and in fact, they are. We only assume we have them, but the details of what's happening there is not described by quantum mechanics. Only assumption that we have them, we can prepare the state. So to understand them, we should go deeper to fundamental physics, which is quantum field theory, which is CPT symmetric. So if having a process for one, there should be also a process for the other, more precisely. So if looking at the system from the perspective of CPT symmetry and performing this process for state preparation, in theory, we should get the symmetric counterpart. Yeah, so I will now show a few examples how to do it. So one example is in electronics. We have a battery which works as a kind of a pump. Yeah, so it both pushes electrons toward the chip into the chip and also actively pulls electrons from the other side. So it works two-way from both directions. So could we do it for some quantum electronics? Yeah. So altogether also two-way two-way control. And so I will talk about silicon quantum dots, which, for example, can encode qubits as in position. So state preparation there is just an impulse, electric impulse to tunnel electrons toward given positions. So could we do it the opposite process? Yes, we could just use the opposite impulse at the end. So from the CPT perspective, it would become the ordinary state preparation process. So now we would get this quantum computer as doing the same from the initial direction, but also the other. And after the CPT symmetric, we replace the two state preparation from both directions, and change and inverse the unitary operator. So, for example, in Wolfram quantum framework, it is available that we have both the state preparation, but also we have this super dagger. You can also do this CPT analog of state preparation. So we can do both. Yeah. So at least here we can already simulate it. And in theory, it will allow for to attack post BQP. that means it contains NP, so we could, in theory, solve NP. However, it would be more difficult than Shor algorithm, which for now is not practical. The record, I think, is 21 still factorization. So the big question we'd like to research, and also we have the team for this two-way quantum for X prize, like 10 persons. To what in practice could we do? So assuming that we have this operation, and what improvements of performance could we reach having it, and also how to organize some experimental tests to show that it is possible. Okay, so what is the CPT? CPT symmetric. So it is at heart of quantum field theory, which is deeper than quantum mechanics. It is, there is this Schwinger's CPT theorem saying that it holds for all physical phenomena. More precisely, any Lorentz invariant quantum field theory with Hermitian Hamiltonian must to be CPT symmetric. So there are some articles, for example, saying that if it's violated, then the Lorentz invariance would be violated also. There is this famous Stackelberg interpretation that antiparticles can be interpreted as traveling back in time. That we can look at Feynman diagrams literally also. So there are lots of confirmations of this symmetry, and so far all are successful. However, they're only in microscopic level. So from more practically, do we have some processes which have the CPT analogs and which we could use for quantum computers? And yes, the lasers are based on this stimulated emission absorption equation. So we have these two equations which in fact differ only by this time direction. So one says that if shining light on some object, the number of excited atoms N2 grows according to this energy density, and the second is stimulated emission. That we have also the opposite behavior, and they are symmetric. The coefficient is the same. Yes, in a few approaches quantum computers, we use for state preparation consequence of this equation inside laser. So if preparing the situation that we use consequence of this equation, instead to try to, we should be able to get the symmetric counterpart part of state preparation. I will show a few examples of that. We have this problem that while the fundamental equations are believed to be CPT symmetric, the solution clearly is not, especially in the second law of thermodynamics, and entropy grows. However, it's not a problem that we have equations which are symmetric, but the solution is not. For example, we have this surface of lake, and it is symmetric in equations. However, if dropping a rock, the solution is no longer symmetric. Yeah? So it's quite standard situation that equations are symmetric, but solution is not. So the question is, what was this rock for our physics? And we can, for example, think about Big Bang as it, because everything was localized, so entropy was low, and it created the entropy gradient, the second law of thermodynamics we observe. So it is a property rater of solution, not equations governing our physics. Okay, so from philosophical perspective, we need to think about time. So there is this intuitive philosophy, so-called presentism, that we have some past situation and it evolves toward future. It is natural for us. However, both the quantum mechanics and general relativity require a different philosophy, which is called eternalis block universe, that we have kind of, let's say, boundary conditions in both directions, and based on these conditions, we have Feynman ensembles of scenarios. We have action minimizing shape of space-time in general relativity. So we have kind of, there is some already found solution in 4 dimensions, and just travel to this solution. And this solution was found through these Feynman ensembles, through action minimization for general relativity. From perspective of, I will briefly show some Gedanken experiments, thought experiment.
Sorry.
Yes.
Excuse me. I wanted to ask, would you clarify the eternalism philosophy for quantum field theory? It's not so obvious.
Yes, so just Feynman ensemble. also defining S matrix, you use some amplitude from the past, from the future, and there's some unitary evolution between. So imagine that you have the boundary condition, and based on this boundary condition, you assume Feynman ensembles of histories between these boundary conditions. I think it's
But
the
that's
same.
Newtonian. Yeah, but that's Newtonian paradigm, right?
So if you use action minimizing, so one history between them minimizing action, that's classical mechanics.
Yeah.
General relativity usually is found this way. However, if you assume Feynman ensemble among such histories of between these two boundary conditions, then it's Feynman ensembles, Feynman field theory. These Feynman ensembles can have various scenarios with creation of particles, annihilation, and so on. So generally,
Okay.
scattering theory, we assume the boundary conditions and assume some unitary evolution in practice expressed through Feynman ensembles of the diagrams, yes, scenarios.
So I can understand that for general relativity, but it's a little bit weak for quantum computing. So sorry for the interruption.
I'm just saying that both the quantum mechanics, quantum field theory, and general relativity both, in fact, require an analysis. The present is our intuition, but physics later requires an analysis, philosophy of time.
Okay, I'll look into it. Thank you.
Can I ask a question?
Sorry.
Sure. From the thermodynamical point of view, to make the process to be reversible, it must be believed to be quasi-static. What is with emission and absorption from this point of view?
So yeah, so we have in fact three equations. So there is also spontaneous emission. So spontaneous emission is kind of this second law of thermodynamics, this entropy growth. However, the two equations, the absorption and simulated emission equations, are written here. If you just change the sign of time, we switch the two equations. And so also we can see that the CPT symmetry requires that this coefficients is called Einstein coefficient B12 has to be equal to B21 because they are replaces in CPT symmetric that they are switched.
Okay, thank you very much.
Thank you. Okay, so there is some, I think, nice thought-provoking thought experiment, Grand experiment, in theory allowed by general relativity. So in general relativity, it's not probably realizable, but in theory there are possible wormholes, and such wormhole could be glued as inclining the bottle in the non-orientable way. So, for example, that traveling through such wormhole, the light cones of past and future would be literally switched. So if there is a quantum computer inside such rocket, after traveling, it would, instead of state preparation, it would use this counterpart of state preparation, the symmetric analog. Yes. Also, the two equations, as there will be change of time, the two equations will be switched. So from the perspective of this observer inside the rocket, the laser would cause excitation of the target, but from the perspective of the external observer, the laser would cause its de-excitation. Yes. So instead of increasing the number of excited atoms, the action of laser from a perspective of this external observer would cause the excitation of this target, because the two equations would be switched inside. So I recommend thinking about this thought experiment. What would happen with a laser inside such rocket which had traveled through this time reversing non-readable wormhole? But it's just thought experiment, but only suggesting that, assuming general relativity, in theory, you should be able to create this symmetric version of the state preparation. Okay, so inside this rocket, some standard one-way quantum computer would be kind of reversed. Yes, so it would use state preparation in the future and reverse measurement in the past. So it would be quite strange, but it would not be stronger quantum computer. It would be still as strong as standard quantum computer. So to get something stronger, we need to use both. We need to have both state preparation and this reverse version of the state preparation. So it's not practical way, this wormhole, but I will show more practical ways in the next slides to reach it. So assuming that we have both state preparation in the past, but also this is symmetric version, conjugated version in the future, like here. So for example, here is a very simple quantum circuit which allows for this 0, 0 and 1, 1. And now after literally enforcing 0 here, we have forbidden this 1, 1. So the only 0, 0 has survived. So this is from mathematical perspective, this is just taking unitary operator, the proper action of this quantum computer, and multiplying it from both directions by some vectors. So here is some mathematics perspective. So we have two set of qubits. The first set of qubits is to be enforced by this CPT analog of state preparation, and here is to be measured. So we have this, we have prepared this state, and now we multiply from the second side, and so this way we should get this kind of state. Yeah, so we literally do the same multiplication, but not only from the one direction, but also from the other. If you can do both, in theory, we should get much more powerful quantum computers. Okay, so let's look at the various technologies and how we should be able to get this conjugation of state preparation. So, for example, silicon quantum dots, they are very popular, especially from Intel perspective. Last year, they have shown 12 qubit such quantum computers. So it looks like this, that they have this standard lithography process, nearly standard, and they can make these qubits inside this lithography. So they use qubits as they encode qubits in position or spin. So if it's in position, as mentioned previously, we could just, the state preparation is just impulse to make 10 electrons to given position. And if doing the opposite impulse at the end, from perspective of CPT symmetry, we would get exactly the same state preparation, but this symmetric version. Yeah, so as all the operations here are performed with electromagnetic impulsor fields, these are relatively trivial to reverse. To make that, looking from the other direction, we get the original state preparation process. For spin, I think there is usually use this Elzerman readout, so they can prepare situation that the only one spin direction can tunnel. So for example, we can help with this tunneling with this impulse, and we can again we can do this such impulse at the end, so that from perspective of CPT symmetry we get the original state preparation process. Yes, so we'd like to just recreate the state preparation, but from perspective of CPT symmetry. And see, and if it is done by electromagnetic fields, it should be relatively easy. So then there are these topological quantum computers that are more hypothetical. However, the last year Quantinum and Google, also Microsoft, they're claiming some successes in realization, and they are very, very time symmetric. Yeah, so the past and the future looks very similar. In the future, they want to annihilate with pairs, but if you would like to annihilate with a chosen value, the chosen particle, then we should be able to kind of enforce this finite value. So there are literally paths in space-time, and we try to enforce them from both directions. More practical are all the state preparations based on optical pumping. For example, quantum computers based on ions, on neutral atoms, on these nitrogen vacuum centers. So they use pumping like shooting with laser to enforce state preparation 1. So the question is how to do the symmetric version. Yeah, so we need to do something like that we do this 1, but from perspective of CPT symmetry. And in theory, we should be able to do it using unidirectional laser. So there are ring lasers with so-called optical pumping, in which the photons travel in one direction. So having such laser, looking from CPT perspective, this photon trajectory would be reversed. Yes, so the photons. So in standard setting, the photons travel this direction, and they excite target on the right for state preparation, standard state preparation. But looking at the situation from CPT perspective, the photon trajectory would be reversed, so it should excite to perform state preparation for the target on the left. So this way we should get the CPT analog of state preparation. Yes. So here you would put the ions for standard state preparation, and on the left we would put ions for this CPT analog of state preparation, which from CPT perspective would look like the original state preparation, or from looking at the equations. So the excitation of this target is a consequence of spontaneous of stimulated emission inside the laser of one of these equations. So we just need to switch the equations to the other to get the reverse effect. Yeah. So that's the big question. So we're having this laser. It produces photons which should be absorbed by this target. So exciting this target. So this equation should act on this target. And the question to test experimentally, I would like to organize such tests, but it's not so simple. Is the question is the second equation, the symmetric equation, acts on this target. So one argument is that looking at CPT per perspective, the two equations will be switched, and indeed the original the excitation equation should act on this target. So in another perspective, this equation should act on this target. Another argument is that adding these a few mirrors to make also these photons go detour around. Both the targets would become the internal target. So two equations should act on these two targets if adding the mirrors around. However, the mirrors alone only add the one equation, the absorption equation. So the second equation should act already before adding the mirror. Yes. So that's the main argument I would like to test. I think it's relatively simple, but it needs to be realized finally. I think it's close to do it in Krakow. However, there are some technical problems. Okay, so another direction is like as mentioned at the first slide, is that we have these pump-like settings that we have kind of pump like battery, and it both pushes electrons into but also pulls actively from. So in hydrodynamics, we have very similar setting as standard pump, which both pushes with positive pressure fluid and but also pulls with negative pressure this fluid. Yeah, so they are kind of similar settings. The question, could we recreate this setting in some electromagnetic setting or photonic? So the equations for hydrodynamics, especially for superfluid without viscosity, are really the same for electromagnetics and hydrodynamics. So the main difference is that one uses speed of light propagation, the second uses speed of sound propagation. But generally the equations are very similar. So in theory should be possible. And another argument is that having this unidirectional laser as previously, for photonic quantum computer, the state preparation is performed by laser impulse. So here we perform this laser impulse. However, looking at it from CPT perspective, the photon trajectory would be reversed. So we would perform the same impulse from the second direction. Yeah. So now we both make the state preparation and CPT analog at the end. So kind of pumping the photons through this photonic chip, both pushing photons into, but also kind of actively pulling photons into. So it is possible for fluid. The equations are nearly the same, so it should be possible. Also, from CPT perspective, we literally switch the two ends of this strip. Okay, so here is some summary for various technologies. So for superconductors, unfortunately, most of them state preparations use thermalization. So for thermalization, we cannot do the reverse version because it would violate the second law of thermodynamics. So in this case, in this moment, I don't think it can be reversed unless having some state preparation with some optical pumping. However, for the rest, I think it should be doable to reverse the state preparation process, which is mostly the optical pumping, or for photons, also like this kind of pump of photons through. So most are these. So standard ring laser should allow for the state preparation here. So looking at CPT perspective from this setting, we would get the same here. Yes. but it's conjugated because of it's from CPT perspective. Yeah, so these unidirectional lasers are look natural to try to reverse the process used for state preparation. Okay, so what would be the consequence? So now there is this very large investment in quantum computers, and one of direction is breaking RSA. And in theory, having two-way quantum computers, in theory, we would be able to attack NP problems. So much more powerful computers. So ideally, being able to attack NP problems, you could break nearly any cryptography. So it would be very, very dangerous. So also we should think about maybe next generation post-quantum cryptography, which could be resistant to such imperfect quantum NP solver. But I believe it is interesting the direction to improve this race to superiority of quantum computers to try to reverse the state preparation process. Okay, so some introduction from complexity perspective, maybe too simple, but okay. So we have some complexity classes. The P as there exists polynomial time algorithm, and P that there exists non-deterministic polynomial. So there is a polynomial time verifier which can say that if given input is right or wrong, and the question is there input which satisfies this verifier? Yeah. So trying all the inputs, you would have to test exponential number of inputs. So it would be costly. The question is if you could speed up this process. And NP-complete is this set of NP problems which can be transformed one into another in polynomial time. And the most famous, no, there are many interesting problems, but from this perspective, I think the trisat is the simplest here to show theoretically, but finally maybe a different one would be more practical to attack with such a two-way quantum computer. So in trisat we have just these alternatives of three variables. Some can be negated, and the question is, could we choose values for which all the alternatives are true? Yeah. If there exist these values, so that this is true. So we don't know if it's polynomial or not polynomial. People try for decades to solve it, and I think most have gave up it. Now, so the question is, could quantum computers, and again, standard quantum computers, we don't know, but probably they cannot. So standard, we can solve BQP problems. So in polynomial time, with some reasonable error probability could solve. So for BQP, there is the most interesting problem, which is in BQP, but not in P, is the factorization, which is at heart of RSA cryptography. Yeah, so here is the factor, not in P, but in NP. So yeah, so having two-way quantum computers, I'm showing in a moment that in theory we could attack also get out of the so at least solve the NP problems. The question is what's happening outside. I think it's not well understood. So if you could get outside, so the more difficult complexity class is the P space. So P space there are solvable in polynomial time. So there are P-space complete problems like the trisat. We've added the for all quantifier. Yeah. So imagine there is also for all here, and now it becomes much more difficult problem. So maybe you could build next gen post-quantum cryptography on these kind of problems, like adding for all here to be more difficult. And so it's basically known that adding this state preparation, this symmetric version is very similar to post-selection. However, instead of selection, running many times, given quantum algorithm, it should be done by constraints. We literally apply physical constraints to enforce not only the initial values but also the final values. So it is known that for selection there is this class post-BQP which contains NP problems. So here it's probably the same as for this two-way, but now we instead of selection, so selection is not practical because it would require exponential number of runs for difficult problems, for NP problems. So being able to do it if constraints in single run, we indeed should be able to solve NP problems. Okay, so let's look at the Shor algorithm. So in Shor algorithm, we start with state preparation of zeros. Then we use the Hadamard gates to prepare the superposition of 2 to the power n inputs. And then we calculate classical function, which is the power in Shor algorithm. Then we measure value of this classical function, what allows us to restrict this ensemble to only those having the same value of this classical function, this m here. And after this restriction, it becomes periodic, and with Fourier transform, you can find this period, which gives us hint for the NP problem. So because of not being able so it being able to also modify the value on the right, also already in Ising model, idealistic, we should be able to attack NP problems. And there are many ways to do it. But maybe let me skip it. Okay, so let's now look at this two-way quantum computer, how to solve NP problems. So it's very similar to this Shor approach, that we prepare a superposition of all exponential number of inputs. Then we calculate classical function, which now is just calculation of this verifier, like this alternative, this conjugation of alternatives. Yes, so we ask if this input is proper or not. So and then instead of measurement here, we would like to enforce only the proper values. So this way we should be able to restrict the superposition to only those having satisfying the verifier. Yes, this condition, for example. So then we just measure the input qubits and we get solution to our NP problems. So in theory, it should be able to attack NP problems. However, it would be more difficult than Shor. So Shor is not very practical in this moment. So the question is how to do something practical with this kind of new operation, also to show it is possible experimentally. Well, that's an open question. So there are many directions to try to do it. For example, better error correction, having this kind of enforcement on here. So for example, you could try to use error correction that we use only code words. We can, in theory, we could enforce only using code words. So we would have superposition of code words by enforcing the syndrome of error correction to be zero, let's say. So that's the question. What practically could we do it? Because unfortunately, this kind of scheme is not practical, but maybe very strong error correction, maybe it will be practical. It's open question to be researched. Okay, so here is some summary that one-way quantum computers allows to break RSA. Having two-way quantum computers, in theory, we could solve NP problems. In practice, the question is open. Could we do it? But maybe it would be safer to try to start thinking about next-gen post-quantum cryptography, also resistant to imperfect quantum NP solver. Yes. So here is some different view on these two algorithms. So we have product from both directions. So having a prepared state, we can also multiply it from the second direction. So here is the Shor that we prepare the ensemble. Then we calculate classical function. Then we measure value of this classical function. Then we use QFT. So we find the period, which gives us hint for the factorization problem. Here is similar for the trisat attack. So again, we prepare the ensemble of our inputs. Then we calculate the verifier. Then we enforce this verifier to be true. And then we measure this value, which would have, in theory, solve our NP problem. Okay, so this is the next part of the talk. A few experiments suggesting this time symmetry of quantum mechanics. So one is the famous Wheeler experiment that So here is a very nice experiment that looking. Imagine that you have far away. You have some a star that the light can travel from one direction of this star on the second direction of this star. So having a telescope which can distinguish these two paths, we would have classical behavior. So here is a good telescope which can distinguish them with classical behaviors of classical statistics. However, if our detector cannot distinguish these two paths, we would have interference, quantum interference pattern. Yes, so after these photons have already traveled here, we make this choice, choosing between classical and quantum behavior for these photons. But now intuitively it should be made, this choice should be made earlier, but then we can make this choice, what's happened here after the photons have passed this position. So this is a photo experiment, and there was the realization by Aspects Group in 2007, which used this Mach Zehnder experiment, which has lifted or not this half mirrored half silvered mirror after the photon has already passed this first beam splitter. Yeah, so when the similar photons has passed here, so having classical or quantum behavior, then we choose should it be classical or quantum, and it worked. Yeah, so indeed, so if it is lifted, then we have 1/2. If it is here, then we have interference patterns, and all photons should go to D2. Yeah, so we can change what photons has done in the past in this intuition. Yes. Another experiment, very nice, from Weidman group, 2013, asking photons where they have been. That they have mirrors with piezoelectric vibration. So in the frequency, they can encode if this mirror was visited or not. Yeah. So here they can see frequencies of the two mirrors, A and B. So the most interesting is so in this setting they see all the mirrors. Yeah. So the frequencies for all the mirrors. However, this is the most interesting setting, that they see ABC. However, the photons only travel to C. Yeah. So the big question is why they see B and C here. Yes, because in theory the photons don't travel here. And the explanation is that we should use this two-state vector formalis, that as in this S matrix, one amplitude comes kind of propagator from minus infinity to now, and the second from plus infinity to now. And the three mirrors are exactly those for which the photons travel from both future forward in time and backward in time. So indeed, we should see these three mirrors. Another very nice experiment. There are these various quantum eraser experiments, and here is the nicest one by Valborn. So they have these two the entangled photons, and they rotate this polarizer, changing statistics between this statistics and this statistic for this double slit here. Yes, so rotating here, we change the statistic. They change statistic here. So again, from causal perspective, the causality kinds of go back in time. So again, it uses this time symmetry intuitively. Okay, so what kind of symmetric analog for photons? So while naively shooting a laser, we hit up a target. There is also optical cooling. By naively we push target by transferring the momentum. There is also optical pulling, optical tweezers. Both cooling and pulling was awarded Nobel Prize. So generally, the radiation pressure for photons is given by this formula, and this is a vector. So this vector can be toward a surface, can be positive, but can be also outside, can be negative. So there is no problem with negative radiation pressure. We can both push with light, but also in theory we should be able to pull with light, and there are some articles about negative radiation pressure, for example, to pull solitons. And there are these two equations, simulated emission absorption, as mentioned before, that there are symmetric, that, for example, in this rocket, which has traveled through this time reversing wormhole, the two equations will be reversed. So also inside this rocket, this pushing with photons would become pulling with photons. Yes, so the sign of this P would be reversed. Okay, so there are a few ways, a few situations that we could, looking at CPT from CPT perspective, the photons should be reversed as previously, but maybe let me skip it. My time, I think, is running. So here is the experimental test I would like to realize. So in Krakow, there is this kind of laser. However, it is broken now, and so we would like to repair it and try to perform this test. So the big question is, we have these two equations. So we know that this equation acts on this target. The big question is if this equation acts on this target. So it is required by CPT symmetry, but from CPT symmetry perspective, the photon trajectory would be reversed. So this equation should be act on this target. So in standard perspective, this equation should act on this target. Yeah. So that's the big question. Is CPT symmetry still conserved in macroscopic scale? So there are two hypotheses we would like to distinguish by experiment. So one is saying that only absorption equation acts. So only this is it doesn't. And the second, that in CPT perspective, it still works as it should. So this equation should act. So we can calculate. So it's not so simple to test because we need this laser and we need to constantly. So while here we increase the number of excited atoms, here we would like to decrease the number of excited atoms. So to decrease, it should be, we need to excite it initially. So this target would have to be excited from using some external laser. And then we should test if turning on this laser, we decrease the number of excited atoms. And it can be calculated by using the two formula, and the difference is this. So the question is to distinguish these two population levels differing by this number. So we would like to organize this experiment to test if this hypothesis is true or this hypothesis is true. So if the first hypothesis is true, it would say that in CPT perspective, the photons should travel the opposite direction, but they do not excite these atoms. So there is some problem with CPT symmetry. So maybe CPT symmetry is only true for microscopic physics. Maybe it's validated in macroscopy. So it was not tested for macroscopic physics. So it would be also very interesting if it wouldn't work. Also, if it wouldn't work, still different approaches for this conjugation or state preparation could work. So it will only remove this one approach. So there are some new applications like these better quantum computers if it would work. So here is this pump analogy. So we have this laser. You would like to use this kind of push the photons through this chip, this photonic chip, which has state preparation with impulse. So here you would like to have the same impulse from the CPT perspective. So we both do this impulse here, but here also impulse opposite. So for example, in this rocket traveling back the opposite, the two impulses will be reversed. Yes, so we push here and pull here. It's such two-way quantum computer. Okay, so here are some different ways. So the question is, so there are many suggestions that we should be able. There is this similarity between electromagnetics and hydrodynamics. So in theory, we should be able to also not only push with light but also pull with light. So you can imagine that we have two pipes in hydrodynamic setting, and we could just watch from which pipe the fluid flows. But we could also pull with negative pressure from the chosen pipe to try to enforce that the flow will be here and not from the random pipe. And there are also considered quantum computers based on the superfluid. So if building some quantum computer based on superfluid with mechanical qubits, then to get to a quantum computer would be just connecting it to a pump. Yeah, so then it would be trivial to get to a quantum computers. So this is another direction how to reach it. Okay, so some general scheme again. So this well-known scheme for one-way quantum computer. So here you would like not only push into some information, electrons, so photons, maybe superfluid and so on, but also actively pull from some side pipes. So here is some slide about this similarity between electromagnetism and hydrodynamics. From mathematical, it's very similar. And I have two more quick slides about the similarity that also the quantum effects are very similar. So it was proposed by Michael Berry the famous one, that the Aharonov-Bohm effect has also had a dynamical analog that we have to interpret the vorticity of fluid as the magnetic field, and you get practically the same. So some of them are for fluid, some of them for electromagnetics, and they look very similar. Oh, there is also this Zeeman-like analog for hydrodynamics. They have bouncing droplets. These CUDA-like experiments. So we have some fluid, bouncing droplets, and it has quantized orbits because then the coupled wave has to become a standing wave, and rotating one direction on the second. Then we get Coriolis force, which in this analogy is the Lorentz force, and we get the Zeeman splitting. They get Zeeman splitting literally. So through Coriolis force as Lorentz force. So these analogies can be indeed taken much further. Okay, so I had one philosophical slide at the end. So again about this symmetry, but now from the perspective of the Born rule, Bell inequalities. So that's the big question: where this Born rule, the squares come from? And as mentioned, from this symmetry in scattering matrix, one comes from the one direction, second comes from the second direction. You have to meet in this position. Also in two-state vector formalis. In this experiment, asking photons where they have been, and also having, let's say, 0-1 range and having some random walk in this 0-1 range. So standard random walk would say that you should expect uniform distribution for this walker. However, in quantum mechanics, we expect this sign square for infinite potential well. So if we assume a uniform ensemble not about points, but from entire paths. So assuming paths toward one direction, we will get first power, so sign. So the probability would be first power. Thinking about trajectories from now toward future uniform ensemble, or from now toward past, and when using full trajectories, we get the square because we intuitively would have to get it twice randomly, one from the past, one from the future. So to get a given position, we need to get the square, the Born rule. So again, the square comes from time symmetry. I think it's the only way to explain it. And having the square, we can violate the Bell-like inequalities. Yes, because so in standard intuitive probabilistic, we have this Kolmogorov theorem that the probability of alternative is just sum of probabilities, and Born rule says to replace it with this Born rule, sum of amplitude and square. So they are completely different. Yes, so inequality derived with the Kolmogorov can be violated with if replacing this rule with another rule. This is nothing strange. So there is this Mermin's inequality I like to use because it's much more crude than Bell, because it's just tossing three coins at least to give the same. Yeah, so having three binary variables, probability that some two of them are equal has to be greater or equal than one. It is trivial to prove for any joint distribution for these 8 possibilities using this Kolmogorov third axiom. But when we switch to Born rule, we can, and using this kind of amplitude, we can violate it to 3/5. So we can also do it in Boltzmann path ensemble, for example, in Ising model. So having Ising model a sequence of 3 spins with interaction enforcing this amplitude, so forbidding 3 zeros and 3 ones, then this would be probability at the end of these half paths. So at the end of this sequence, we would have this probability, so uniform distribution among all these possibilities, 6 possibilities. However, in the center, we have to multiply. We kind of get it twice. So as here, you would have the square, and which would allow to violate this inequality if measuring only 2 out of 3 spins. So we measure only 2 out of 3 spins. The third remains unknown in the Boltzmann ensemble. Yeah, so then we get the violation of this Mermin inequality. Thanks of replacing third axiom with the Born rule, which comes from the squares, which our arguments suggest come from time symmetry. Okay, so maybe so here is about the thermodynamics. So again, philosophical more. So we have the equations which are believed to be CPT symmetric, but the solution is not, and what is not, nothing strange. So the question is where this entropy growth comes from. So in classical evolution, there is no probability, so entropy is zero. So to get the entropy, we need to average. So it is called approximate with some mean field approximation. So average over the trajectory, average make some smoothing. So generally, this approximation is called Stożer-Lenz. So before this approximation, we have entropy zero. There is no entropy growth. We have unitary evolution of wave function of the universe. But after to get entropy growth, we need to perform this approximation. For example, here is this, so we have this containment with particles. I think from classical perspective, we have this Poincaré recurrence theorem. So we can get back to this original setting that all of the particles are in one part in finite time. However, if we approximate it with just one parameter, that p percentage of particles are in the left containment, then we can show that the entropy has to grow after this approximation. Yes, so this entropy growth is consequence of using this kind of approximation, Stożer-Lenz, which allows us to show the entropy growth. However, in fact, it is symmetric. If you know that there is a low symmetric, slow entropy situation, but also evolving toward past, it should also grow because we lose information about the situation. So entropy growth is in fact also kind of symmetric. So knowing some low entropic value, looking about entropy, our knowledge about both future and past, it should grow. We lose information. So here is some summary for various technology. In theory, also there are these mechanical qubits considered, for example, the superfluid. So again, we could, for superfluid, just connecting to a pump. So it should be doable. And this summary that here is this basic approach using this unidirectional laser, which performs state preparation here. So from CPT perspective, should perform state preparation here, which is this conjugated version of state preparation, in fact, because it is in CPT perspective. And the final slide. So we have this group, a few persons for the X Prize group. So if somebody is interested in collaboration, so please let us know. There are obviously many questions to answer. So finally, the most important is, could we get it in some technology with experimentally? Yes, so that's the most interesting question. And so try to organize some confirmation, but it's very difficult to get such experiment. I think that laser is just the simplest. Then there are many questions. Having such operation, what in practice could be made? So sure is so this approach is too difficult to attack NP, but we need something smarter, maybe some improvement of, let's say, error correction, of adiabatic theorem, maybe to take some current supremacy claim and try to prove its performance by adding this kind of operation. So that's a difficult question. What direction we could try to improve? So maybe we could try get some new ways of thinking about quantum computers after that. Yes, improvement of current supremacy claim by adding such operation, maybe they will be more practical. Finally, which NP problems to attack, maybe add some error correction to be able to do it. Then finally, what is the complexity class? So it's very difficult, and there's a lot of research, but so it is somehow between NP and P space, where exactly we don't exactly know. And so this maybe P space based post quantum cryptography, I think it's very interesting direction to find a cryptography which could be resistant to such potential quantum computers. And different applications finally in test. So thank you very much for attention. I have finished.
Sorry, I was not able to unmute. Okay, thanks. Thank you, Eric. Thanks for a great presentation. And yeah, now it's time for questions. And I see two questions on our chat. So let me just read the first question. Sorry, I have some technical issues with Zoom now, but anyway.
I see the slides.
Okay, so yeah, there's the first question from Mohammad Reza. Isn't the functionality of quantum field theory, for which CPT theorem truly demonstrates itself, mostly reserved for high energy phenomena? At the face of it, it is quite nice to use fundamental physics, but then you have to deal with the effects, pair creation, etc., right? Also, are these qubit modalities at all appropriate for high energy domains?
So I don't think quantum field theory is generally believed to cover all physics beside the general relativity. So I don't think it's true that it can be only applied to high energy physics. So for example, this connection, there are various corrections found with the QFT. So it is believed to be so quantum mechanics is believed to be effective approximation of quantum field theory. That in quantum field theory we use ensemble of Feynman diagrams. So we allow for pair creation, annihilation, while in quantum mechanics we have fixed number of particles. So quantum mechanics is only approximation using fixed number of particles, and but generally there are also lamp shift. I think is calculated with quantum dynamics. Yes, so it QFT is also applied in the low energy physics for corrections. So it is believed to be the lowest.
Okay, thanks for the answer. Mohammad Reza, does it answer your question, or do you maybe have a follow-up question?
So it yeah, it applies. Generally speaking, it applies, but I'm not sure if we're not proceeding with the low energy domains we're supposed to high energy phenomenon, because ultimate design for those domains, I would say I have some doubts. Yeah, so, I understand the lamp shift and the directions of dynamics. Those are all justified, but still see if it would apply to quantum computers right now. But that's my opinion.
Generally, quantum mechanics is usually thought about as effective approximation of quantum field theory. So the lowest level we know is quantum field theory, which is CPT symmetric. So if having a process for state preparation, it is in fact done in QFT. So if doing the same from CPT perspective, we should get the conjugated version of state preparation. So there was this assumption that we have state preparation, but not the symmetric counterpart. So the question is, what are the arguments for this assumption? And I don't know any. So somebody in the past has assumed it. Everybody else has blindly followed, but I couldn't find any real argument that we can only use this, but not this. And if there would be such argument, this argument would violate CPT symmetry. So it would be very, very important argument to explore and understand.
So just to ensure that I understood the whole picture. So you are using this philosophy that CPT is applicable in the whole quantum field theoretic domain, and because quantum field theory is the general theory of nature, so you can use to predict algorithms, for example, to generate something like Shor's algorithm, or I don't know, maybe cryptographic, all the cryptographic analysis that comes out after it. So you are using this generalistic natural philosophy to create some interpretation based off nature, right? That's the idea, right?
I'm just using the belief that physics is fundamentally CPT symmetric. what is required
Okay.
for
Okay.
Lorentz invariant quantity theories, intermediate Hamiltonian. If it will be violated, then the Lorentz invariance will be violated. So it is very important symmetry believed, I think, by most of physicists. And if the symmetry is true, and if you have process for state preparation, performing the same process in CPT perspective, you would get the conjugated version of the preparation. So I'm just assuming that physics is fundamentally symmetric.
I understand that. That's absolutely justified. But the physical realization, the devices, the engineering, apparatus that are required to implement these, I'm not sure that they follow with right now, at least. Maybe.
So once again, we need to look at state preparation used for various technologies. And for example, for silicon quantum dots, these are just impulses. So we need to perform the opposite impulse at the end. And that's all. And if you do it, then looking from CPT perspective, you get the original state preparation.
Okay, I should look into it. Thank you.
Thank you. Okay, this was the question about the Intel. Yes, so the 12 qubit is this the tunneling something. It's from the last year, and now I think there was about this 300 millimeter wafers. They can control single electrons in a few days ago.
Can you maybe later share the link or the title of this paper? I can later distribute it.
I could put the slide here. Maybe let me put them so there are the slides once again. So the links are here. I think I want some of these links. So 24 articles. So this is the fresh one, and here I think is the 1 year old.
All right, so everyone can check on the slides. Okay.
Yeah. So there are lots of links in the slides.
Thanks for sharing the slides. Okay, great. Good. All right, do we have more questions to Jarek? Questions or comments or suggestions?
So if somebody's interested, please contact us. So we have this group for X price. Maybe it could be extended.
Yeah.
Generally, some collaboration, especially for the experimental realization, or just think. So if you have an algorithm for post selection, think about improvement when being able to do it in single run. What practical improvement could be achieved this way?
Maybe general comment. So perhaps it's possible to test this type of hypothesis stated by Jarek Duda using semiconductor quantum dots with architecture of a quantum computer that is spin-based or position-based as by Fujisawa. That's one direction. So test by means of semiconductor quantum dots. And another possible angle is probably by superconducting quantum dots. So that's there is certain possibility of perhaps making this test by Cooper pair box junction.
The question is where. So I think it's in Poland. It's very difficult, but in Poland we could test this one. So the test we could perform in Poland is this test. Just ring laser and excitation of this target and control of population of this target, and to distinguish these two hypotheses, which differ by this number. So if somebody could help, has access to ring laser, or there is such ring laser in physics department, but is damaged, and so we need to repair it. If somebody would like to help, so we are open to collaboration.
All right. Do we have more questions or comments? Okay, I don't see more questions now. So Jarek, thanks again for the presentation, and we also thank everyone for attending and for asking the questions, for participating in the discussion. Now I will just present a few last slides just to also tell you about some future plans. So let me share my screen again. And yes. Okay. Okay. I hope you can see my slides now. So yeah, thanks once again for your attention. If you're interested in our meetups, well, here are some links to groups or websites or channels that you can follow to stay up to date. And I would like to thank once again our strategic partners for supporting us and our honorary partners as well. You can also donate our activities if you are interested. If you are in Poland, you can also just give 1.5% of your taxes to support our activities, non-profit activities, of course. And I would like to invite you to attend our next meetup of Warsaw Quantum Computing Group. So it will be in June, on 13th of June. Axel Dayan from D-Wave will tell about D-Wave's technology, so the exact title will be provided later. But it seems that the date is fixed, so save it in your calendar, and we hope to see you next time. So with this, I will stop sharing my slides, and I will also stop recording. Thanks once again, and we hope to see you next time.